Hello my friends and welcome to another video on Physics Paper 1 for AQA GCSE. Here we're going to be looking at the atomic structure, which is mostly looking at radioactivity really, but we need to look at atomic structure and isotopes and the history of the atom before we can go into what radioactive decay is, nuclear equations, half-lives, contamination, and then finally onto the physics-only part where we look at hazards and uses of radiation, fission and fusion. So for the first part here, there's a bit of overlap with chemistry, where we look at the atomic structure and isotopes and what they are. So first thing that we need to know is that an atom has a radius of approximately 1 × 10 to the power of -10 meters. Now that is the equivalent of 0.1 nanometers in size, so they're very, very small. And we also need to know, relative to that a nucleus is about 1/10,000th of the radius of an atom. So the drawing I've got here is obviously not to scale. The scale example would be that if you had a nucleus would be about the size of a pea in the middle of a football stadium on the centre circle, whereas the electrons would be flying around the outside of the stadium itself. So the nucleus is very, very, very small, and an atom is mostly just large empty space. But the extra part that we need to know in physics is that these electrons exist in different energy levels, and these energy levels can be changed, so we can move these electrons between different energy levels. So if an atom, for example, absorbs electromagnetic radiation, the electrons will travel up to a higher energy level. And this explains why things get irradiation and why they absorb and then emit radiation themselves, because they will then cause that radiation to be released again. Probably the most important term regarding atomic structure for this topic, though, is the term isotope, because we need to know what isotopes are to explain why things can become radioactive. An isotope is an element that has the same number of protons, so therefore is the same type of element, but has a different mass because it has a different number of neutrons. Now, that doesn't change necessarily its properties, but it might make that nucleus less stable. Now, before we go on to looking at what instability means for atoms, we have to just look at an overlap here to chemistry and the history of the development of the atom. And these are the stages that we need to know. This is exactly what you need to know for chemistry too. It's just that we focus more on the alpha particle scattering experiment than perhaps you would in chemistry. It's probably the same though. But anyway, in early thoughts of what atoms were, we called them tiny spheres that cannot be divided, so we couldn't make them any smaller, which is kind of true for today. And then we developed a model a bit more, so we looked at creating something called the plum pudding model, which is this one on the right here, where you had a ball of positive charge which was interspersed with so the whole of the area around these negativity was positive, and then dotted around was negative electrons which were embedded in it. There wasn't anything else to the atom, that's just what we thought it to be. And then this guy called Ernest Rutherford came along, and he set up an alpha particle scattering experiment, which is where he got some gold leaf and he arranged the gold leaf atoms really, really thinly, so 1 atom thick, and he fired some alpha particles at them. Now, the thought was the alpha particles are positive, the nuclei of these are positive. What they expected to see was when these helium nuclei, which is what alpha particles are, were heading towards these atoms, that because of the large positive space within that atom, the majority of these alpha particles would be reflected back, so they'd ping off back to be detected near to where they were sent from. But what they found was that the majority of the alpha particles passed straight through and they came out the other side, and only rarely did we have any that actually were reflected back or deviated from their path slightly. And what that showed was actually the atom isn't mostly positive. In fact, most of the positive charge is found concentrated at the centre of the atom. And that's when we decided to call it a nucleus and figured out the scale of the nucleus as being about 1/10,000th of the total size of the atom. So we found out the mass is concentrated at the centre and that it's charged, and it was Rutherford that found that. So we need to know the name of the experiment, and Rutherford was the man that came up with that. That led to near enough the nuclear model that we have now. And then a guy called Niels Bohr discovered electron orbits. He basically did some calculations, and his theoretical calculations agreed with later experimental observations, which gave evidence for electron orbits existing. And we then also found other particles in the nucleus, naming the proton. And later a guy called James Chadwick, another person you need to know name of, discovered neutrons. We don't need to know anything about Bohr or Chadwick or the discovering of the protons in terms of their experiments, just what they discovered. So Bohr, the electron orbits, discovered a proton, and then we had Chadwick who discovered neutrons. So if an isotope is unstable, what's going to happen? Well, an unstable nucleus is going to give out radiation to become more stable. And this is what we call radioactive decay, the thing that's being lost as a result of it becoming more stable. Now, at this point, it's worth us noting what a rate of decay is measured in, and it's measured in a unit called becquerels. And this count rate can be detected by using something called a Geiger-Müller tube. Okay, so on to what these types of decay are. An alpha particle is the biggest and the most harmful if you give it the right situation, right circumstances. So this consists of 2 neutrons and 2 protons, and that is released from the nucleus. That's a lot of stuff that's released. It actually has the equivalent mass and proton number of a helium nucleus, so it is actually the decay and the release of a helium nucleus. Now this has a very high ionizing ability. So it has a very strong ability to remove electrons from something that would collide with, causing it to become an ion. So it's very, very large chunk of mass that's very positive, flying at high speed. Now, because it is highly ionizing, it has a very low penetration. It's not able to travel through much air, so very short distance, like centimeters, and it will even be absorbed by even a sheet of paper. So as much as it's very ionizing, it's very dangerous. Actually, it won't even go across your skin. But if it got inside your body, then it could do real harm. A beta particle, in contrast, is a high-speed electron that's emitted. Now, the strange part of this, though, is it's emitted from the nucleus, and there aren't any electrons in the nucleus. So where does it come from? Well, it comes from a neutron, which has a neutral charge, turning into a proton. And as it does that, it emits an electron. So neutron is a neutral charge, it turns into a proton, which has a positive charge, and it releases an electron. And that electron is the part that's being lost to make it more stable. And so the way that we would write this, it has a mass number of 0, and it actually has a proton number of -1, because we're creating a proton in the nucleus of the thing it's being ejected from. A gamma ray, in contrast, though, is not a particle. So you can see alpha particle, beta particle. A gamma ray is just energy. It's electromagnetic radiation from the nucleus. It's just energy. It is not an actual particle. And what it means is the nucleus that was unstable becomes a little bit more stable because it's just lost some of its excitement, some of its energy. And the final one that we need to know much less of is a neutron. A neutron can be emitted too, just to make it more stable, but we don't need to know anything about how it can be passing through, its penetration, its range in air, and its ionizing ability. So the highest ionization was the alpha particle, and the lowest ionization was gamma ray. So we're going from the most to the least, the beta being in the middle. The penetration, though, is the opposite. So the alpha particle has the least penetration, so it can barely travel through air, it's absorbed by paper. A beta particle, in contrast, is absorbed by a thin sheet of aluminium, by aluminium, and so that can move through a lot more of air because it's moderately ionizing. But a gamma ray is a low ionizing ability. So it can travel through a lot more. So it's going to travel through many meters of air, and it will travel through a significant amount of, or get stopped by a significant amount of lead, or a significant meter to 2 meters of concrete. So it's going to get absorbed by those. Absorbed by lead, Pb. So the typical kind of question they might ask you about alpha, beta and gamma is about their ionizing and penetrating ability, but the second thing that they can do is ask you to write nuclear equations for them, which are like chemical equations but showing how things decay. So if we start here for alpha, we could have uranium-238, which has a proton number of 92, and if it decays creating alpha decay, it's going to release that alpha particle, which has a mass of 4, a proton number of 2, and we call it a helium nucleus. You could also write it as 42 with the alpha symbol, but they prefer it to be a helium symbol because that's really what it is. Now, to work out what you're going to get from the uranium here, we have to take away the 2 protons from the 92 of the uranium and the 4 mass from the 238. It's easy as that. So we're going to get 234 and a proton number of 90, and that gives us thorium. And you'll usually get given the information that you need to figure out what that end element is. You don't need to just magic it out of nothing. So that's alpha. For beta, it's slightly different. So beta, let's look at an example of carbon-14. So carbon-14 has a mass number of 14. As I said, it has a proton number of 6. And if it goes through beta decay, what we're getting out of it is something that has a mass number of 0. One of its neutrons is turning into an electron and a proton. It's firing out the electron, hence this is becoming our electron, which is fired out very quickly. And as a result, the proton number has gone up by 1 because we've lost a neutron because it's turned into a proton. So its proton number has gone up by 1, but its mass number has not changed because a neutron has a mass number of 1 and a proton has a mass number of 1. So we've got exactly the same mass as we did at the start. But as a result of the proton number changing, we've got to now see that it's a different type of element. So it's actually now changed into nitrogen. So alpha decay makes the proton number go down, so you're working your way down the periodic table to thorium. However, for beta decay, you're actually working up the periodic table. The number of protons it's getting is becoming more. So it's turned from carbon into nitrogen. For gamma, however, if we had carbon-14, again, if it released gamma radiation has 0 mass, it has 0 protons. All it is the release of some energy. So you had carbon-14. If you imagine carbon-14 here was slightly more energized, slightly more unstable, well now it is happy carbon-14, or happier carbon. So now we've looked at how things decay. Let's look at how their rate of decay changes over time. And this is a term that we'll look at called half-life. So the decay of any individual atom is completely random. We have no idea when it's going to decay. It's a high likelihood that it will if it's unstable, but we don't know as an individual atom when it's going to decay at all. We can never predict it. It might never happen. So the decay of these atoms is random. However, if we have enough of these nuclei of a certain element and isotope, we can predict the time it will take for either the number of nuclei to half or for the count rate or the activity to half, and that's what we call the half-life. The half-life is the period of time it takes for the number of nuclei to half or the count rate to half. So you'll have to either find this out from a graph that you're provided or from a table of numbers that you're provided. And what we need to look for is either the activity or the number of nuclei halving. So any period of time it takes for them to half. So we could start here at 40 and we could see how long it takes for them to go down to 20. So here if we track it down, we're interacting down here at 10 and at 30. So how long has it taken? It's taken 20 seconds for it to half. If we then go from 20 down to 10, so again working down, and you should draw this on the graph to make it clear where you've taken your data from. So 20 down to 10, we've got there 30 seconds and 50 seconds. So again, it's 20 seconds. And every 20 seconds it should be halving. And you could do that from a table in just the same way because you'd have this data instead in tabular format. So at 10 seconds, you'd have 40, a count rate of 40. At 30 seconds, the count rate would be 20, and they usually make it pretty obvious for you. Just look for the numbers that are obviously halving, and then look at the time it's taken for that to happen. Look at the difference in time, and that gives you your half-life. So once we've considered half-lives, how things are decaying, what they can decay into, we need to look at the types of radiation we can receive and the risks and benefits in using them. And the first distinguishing point we want to make is the difference between contamination and irradiation. So contamination is where we have the presence of unwanted radioactive material on other materials. So if you imagine you are working with radioactive sources, if you got some of the source on you because you touched it and some of the metal would come off onto your hand, that would mean that you are contaminated. And the hazard from this is the decay of these materials, because those materials are on you, they're decaying, and the decay is then going to ionize your cells, your DNA. The risk is that actually that decay will lead to damaged DNA or cells or tissues or organs, eventually potentially leading to forming cancer or death or awful burns, that sort of thing. But preventing that can be quite easy. So preventing it is obviously just coming as close as not touching it. So wearing gloves, using tongs. So you might get questions where you need to explain the safety precautions that a teacher demonstrating the use of radioactive sources might have to take. So they'd wear gloves, they'd use tongs. There's certain procedures they would have to follow. Those two are obvious. Keeping it at arm's length away from the body. They're pretty simple. For irradiation, though, irradiation isn't having the radioactive material on you. So if you pointed a Geiger counter at someone that was contaminated, it would be getting a count rate coming from them because they have radioactive material on them. However, for irradiation, if you are irradiated, it means that you've been exposed to nuclear radiation, but you're not actually radioactive yourself. So you aren't, if you pointed a Geiger counter at someone that was irradiated, you wouldn't get any more count than you would from the background radiation. You'd just get the odd pip. So radiation prevention comes down to how can you avoid getting radiation from a radioactive source. So again, the risk is the same. The risk would be damaged DNA, cells, tissues, organs, but the prevention would be slightly different. So safety precautions you might take here. So it's kept in a box, so keep in the box for as long as possible. So only have it out for a period of time that you need it to be out for, and that's it. Obviously don't point it at anybody. So students particularly, if this was a teacher demonstration at the teacher, that's pretty obvious, isn't it? Don't look at the source. Another obvious point. So radioactive sources are in a little housing. Don't look directly at the source because it will be then irradiating your face. Hold it away from the body. Hold away from the body, and again with tongs. For an alpha source, you're not going to be too worried, but for a beta source, it might cause a little bit more damage to you. Gamma source will certainly pass through you. So hold away from the body. You could use tongs, for example, here. You could use or call them forceps if you want to. Any of those are sensible. You could even go as far as saying wearing gloves and wearing goggles, safety glasses, again at this point. It all should be fairly sensible. As much as they are dangerous, we are exposed to radiation all the time, and we do use them in medicine too. And we're exposed to them all the time because we are getting background radiation from things like rocks. So particularly in areas in the country like Devon and Cornwall, where there's lots of granite, that will give out a lot of radiation. The cosmic rays as well are just causing us to sometimes get some radiation and have to work through into the atmosphere. And we also have, from weapons testing and accidents, nuclear accidents, that we have man-made sources of radiation that are being produced too. And so if you set up a Geiger counter anywhere, you would just get ticks as you'd be finding radiation being received. It's not enough to harm us, we think. It might increase the risk of cancer by a slight amount, but really it's so low that actually we don't really need to be worrying too much. But if we did, we could measure our dosage, which is measured in sievert or sieverts, and we have a scale. We don't actually need to know how much about it as a scale, but we do need to know that a millisievert is 1,000th of a sievert, and that is used then to see the impact. So if you had more dosage, radiation dosage, you'd have more risk of cancer, nausea, and eventually going on to being killed by the radiation. But we do use it in medicine as well, so we use radioactive sources quite often to explore internal organs. We typically here use gamma sources, and we use a gamma source with a short half-life. There's a good reason for this. So firstly, the gamma radiation is good because it can penetrate through the skin so that we can detect the source of the gamma, and so see where there are build-ups of blockages in intestines, for example, or blood clots or tumours or whatever we're trying to spot, so we can actually have it inside the body and it will leave. We also want a short half-life so that the source will become inactive very quickly. Just looking at a mark scheme very quickly, the mark scheme would say that we want to cause less damage to cells, so it's there for less time, basically. It's also good because it's got low ionizing ability, so compared to an alpha source it will cause less damage to the cells, but yeah, we want to have it able to leave the body so that we can detect it too. We can also use radioactive sources to control or destroy unwanted tissue, so this is radiotherapy. In radiotherapy we have radioactive sources pointed from a number of different angles, so rotating the angle of where the source is pointing from, targeting a particular tumour or whatever it is we want to try and destroy. With enough radiation dosage, with enough CVER, those cells will die, and so that tumour will no longer be able to grow into cancer. But you know, we're fighting cancer with a potential another source of cancer, so the cells around that tumour have a slight risk of forming cancer themselves, and obviously the medical procedure is followed up with rigorous monitoring to make sure that that doesn't happen. The final two things that we're going to look at in this topic are for physics only, and we're going to look at two nuclear processes. So this isn't decay, this is playing around with whole nuclei, either splitting them in fission or fusing them together in nuclear fusion, so putting two nuclei together. So in fission, what we have to start off with is a large unstable nucleus, so something like uranium, which is already radioactive, it's already unstable, and we basically want to put it to tipping point. So what we do is we fire a neutron at it and we cause it to get absorbed by this nucleus, and that's a key word, you must say absorbed here. So it's absorbed by that nucleus as it becomes even larger and even more unstable. And what that causes to happen is it causes this to just shatter. It shatters pretty much in half. And if you think of something shattering, it's going to cause shrapnel to be released. And so by causing it to shatter, we get two smaller nuclei, which are near enough equal and near enough half. It's not always that way. It can be one slightly larger and one slightly smaller, but it's that way. The other things that we get, though, are the shrapnel, and the shrapnel released are more neutrons. And these neutrons have very high kinetic energy, so the EK of all of these things is going to be high because they are exploding outwards. So high energy, fast travelling neutrons. And we get either 2 or 3 of those. And the nuclear fission reaction can be dangerous and used in things like nuclear weapons, where these neutrons will then go on in a chain reaction to collide with more large unstable nuclei, which themselves will then split, which will then create and release more neutrons, which will then further go on and have a large chain reaction. Now in a nuclear weapon, that's obviously really dangerous, but in a fission reactor, what we do is we put in some carbon rods which will absorb these neutrons, and we can lower these carbon rods more into the reactor to absorb more of these neutrons to slow down the process and to potentially even stop the process if we wanted to. So with a fission reactor we can control how much this process is happening, but in a nuclear bomb we want the chain reaction process to be happening as much as possible. And in nuclear fusion, the only thing we really actually need to know here, and the only expectation we have, is that fusion is a joining of two light nuclei, so small nuclei, to form a heavier, larger nucleus. So that's the phrase we need to use when they're just saying, what is nuclear fusion? It is that joining of two light nuclei to form a heavier nucleus. Bang! There's your marks. Nothing more than that. But in understanding why it's so powerful, so this is what's happening in stars. You'll learn about space in physics in paper 2. This process takes some of the mass that's produced and converts it into energy, which is weird because you've been taught in chemistry about the conservation of mass and all that sort of stuff, and then suddenly here comes some rule that mass can turn into energy. It is magic, and you don't need to understand why or how that happens, and you'll learn more about that in A level. If you want to go and do that, then well done to you. It's really good. Recommend it. But here you don't need to worry. Okay, so if we start for an example of two types of hydrogen here. So we've got deuterium, which has a mass of 2 and a proton number of 1, and we have tritium, which has a mass of 3, proton number of 1. They will fuse together. This requires loads of energy to start it happening. So to force two nuclei together, which are very repulsive of each other because they're both positively charged, that costs lots of energy. But if we make it happen, we can produce a larger nucleus. So here we have helium-5, has a proton number of 2, and you just get loads of energy being released by this process happening. I mean, look up at the sun. Well, don't look too closely at the sun, but it's producing so much energy. It is just releasing it all the time. It's the only reason that we're alive here is because the energy coming from the sun doing this process so frequently. But the weird part about this is that some of the energy is coming from the loss of mass. So we've got a mass number of 2 plus a mass number of 3 produces something like a mass number of 4.98. Some of that mass is gone because it's been lost as energy, and that's a lot of energy that can come from a little bit of mass. And that is it. But again, don't worry, that part is not super important. What is important is defining it as joining of two light nuclei to form a heavy nucleus, and some of this energy that's released is where the mass has been converted into energy. So there we are, the end of atomic structure. Thank you for watching. Again, if it's been useful for you, do like and subscribe. Any questions, drop them in a comment. I'd love to get any feedback.